Great, good afternoon. Thank you for holding up despite the warmer temperatures. Let me start with a shameless advertisement. We have a new journal where I'm editor-in-chief, Journal of Computational Algebra. It's an open access journal. Yes, it is with a commercial publisher. And if you want to discuss it, I'm happy to discuss that. The goal is basically to fill the hole of what the London Math Society Journal of Computation and Mathematics did. It's to have, for example, since publishing modalities seem to be changing again, to have an open access journal in our area. There are no article processing charges for submissions in 2022. Yeah, I would like to invite you, if you are looking for journals, to consider this. Right, so let's go back to where I was at the end of my second talk. I talked about this solvable radical structure, and I will not bore you with this horrible picture of the structure in detail. Basically, what we had constructed for a group is we have a group permutation or matrix group. From the composition tree, we constructed a homomorphism into a direct product of such wreath products. And this image has a permutation or matrix representation, which is kind of nice. The kernel of that homomorphism is the largest solvable normal subgroup, the solvable radical. And the socle of this factor and the pre-image of the socle will be denoted by S star, is a direct product of simple groups. These are the multiple copies of these TI. And this is the data structure which is used for higher level calculations. Namely, what we do is, because the radical is solvable, we can find a series of normal subgroups. So I want them all to be normal in G, such that each subsequent factor is elementary abelian. That is, and my groups are finite all the time. And then the idea is basically, for calculating in the group, we calculate first in the factor G modulo R. That has this special structure. That means often one can almost write down what the result is, or a large part of the result can be obtained from knowing things about the simple groups. And then we lift the result. That is, if assuming we know it for a factor group, we obtain the same result for the next largest factor group, and so on, and so on, and so on. So each time we're adding such a module to it, and adding the module to it basically will reduce to linear algebra on the vector space. And linear algebra might include things like cohomology or so, or orbit calculations on the vector space, but things which one can do. What we need, of course, for linear algebra are bases. And a basis in this context, or the collection of bases, is a polycyclic generating sequence adapted to this series polycyclic generating sequence in the same sense as in Bettina's talk. And I will call these PCGS just to be short. And if you worry about representing factor group elements, basically, I can always work with pre-images in the full group. For describing such algorithms, because this is now an inductive process over multiple steps, it's enough to understand one step. So the situation, the case that actually the radical itself would be already elementary abelian. Okay, the first example I had thought I would do, actually I will skip. It is on the web if you care about, but I think for time reasons I shouldn't go through this on an afternoon at 4:35 or so. So let's look at what does this mean for, say, calculating subgroups. So we have a group. We have in there a normal subgroup n. This normal subgroup n is assumed to be elementary abelian. And by induction, I assume that subgroups of the factor group G modulo n are known. Now, how would I find a subgroup U or of G, or if I look at such a subgroup? Well, the subgroup, if it contains n, it's just pre-image of a subgroup of the factor, then I know it. So let's look at the other case. Then I can look at the subgroup generated by n and u. That is a pre-image of a subgroup of the factor. And I can take the intersection, which is subgroup in both. So A I know, because it's from the previous step. N is elementary abelian. B is subgroup of an elementary abelian group. Well, subspaces are easy to find. So I also know, I know A, I know B, and I know, because n is normal in G, B, which is the intersection of n with U, is normal in U. B is also normal in n, because n is abelian, so B is normal in the group generated by both, which is A. That means U modulo B is a complement to n modulo B in A modulo B. And this is a vector space, so I have a complement to a vector space, to a complement to a normal subgroup, which is a vector space, and I can calculate this with one cohomology. Yeah, that's what we did this morning. And that is basically the process for finding. So assuming the subgroups of the factor are known, I run through all subgroups of the factor. That gives me the A's. I run for each A through all subspaces here, which are normal in A, so basically submodules of n. For a pair AB, I find the possible U's by looking at complements in this factor. What about conjugacy? Obviously, conjugate complements will lead to conjugate subgroups. Furthermore, I can fuse complements under the action of the normalizers of A and B. I can describe this through an action on the cohomology group. And that's basically how GAP calculates subgroups. And just to give an example of this, let's say I take, so what am I doing here? I take SL25 and I take the wreath product of this with S3. That is a group where I then have underneath a 2-cubed vector space. I have a factor group which is basically an A5 wreath 3. And if I calculate the subgroups, it first gets subgroups of A5 from pre-computed stored data. It uses the wreath product structure to build subgroups of the factor. And it does so basically in steps: first to add another copy of A5, another copy of A5, then to fuse them and to look at the action. And then in this step 2, it has a normal subgroup of order 8 and goes through and does this lifting. And yeah, that finds the subgroups. Okay. And other things like conjugacy classes of elements, testing whether elements are conjugate. In principle, even normalizer, though, that is not yet in GAP put in by default because it's hard to compete with backtrack for efficiency. In certain cases, use this. I want to mention one other example, A, because I'm going to use it later on, B, because it uses cohomology. And that is automorphism groups. This is due to John Cannon and Derek Holt. I will talk about automorphism groups. Group isomorphism works similar. And one reason why it works very similar is the observation that if you want to test whether two groups are isomorphic, you could look at the automorphism group of their direct product and check whether that automorphism group has an element which maps one to the other. So that's just conceptually a reason why these two operations are very related. So it's just easier to look at automorphism because you just have one group and not two. It's as with kids. If you are two adults and one kid, you have it fully under control. If it's two, you lose the absolute majority. So again, I have a normal subgroup of, here now the group is called E because earlier it was called E for extension. And because I'm talking about automorphisms, I don't just want an arbitrary normal subgroup. I want one which is fixed under automorphisms. Then that means it is called characteristic, because otherwise, basically, this inductive process would not work for automorphisms. Well, if it is characteristic, every automorphism of the whole group, which is such an extension, induces an automorphism of this normal subgroup, and it induces an automorphism of the factor group, simply by restriction or by acting on representatives and then looking what it does in the image. Not every automorphism of these is obtained that way. It's just some automorphisms. Now, what we do is, again, inductive step, we assume we know the automorphism group of the factor, and we now construct the automorphism group of the whole group in 3 steps. The first step is we calculate a subgroup of the automorphism group, which I call C, which are those automorphisms that act trivially on the normal subgroup and trivially on the factor group. If you write what this means, you get the conditions for a crossed homomorphism, which is exactly the conditions for Z1, the one cocycles. So if you calculate the one cocycles, from that you can immediately write down what these automorphisms are. Next, we take a larger subgroup. That's the automorphisms which act trivially on the factor but might do something on n. However, because we have already C, we need to find only representatives for each action on n. Because if I have 2 automorphisms here which act in the same way on n, their quotient will act trivially on n and will be in C. Yeah? So I only need to find representatives. Well, what are these? These are module automorphisms of n, considering n as a G module, and meet-X style techniques can be used for this. Finally, how do I get the whole automorphism group? Basically, there I need to, at least in the worst case, I need to search through the automorphism group of the factor to find the subgroup of induced images. And basically, I need a test, and I don't write down the details here because that is messy, to check whether an automorphism can be induced or how to extend such an automorphism of the factor. That is the bit which is expensive in the automorphism group calculation. So it's the fact that I need to search through this automorphism group and need therefore to be able to represent it on the computer, which I currently do as a permutation group. So I need to find a faithful, for efficiency reasons, so I need to find a faithful permutation representation of the automorphism group of the factor. And if you have larger isomorphism tests in particular, it doesn't even matter whether it's solvable or non-solvable. That is the bit, that's the bottleneck for the calculation. And yes, if the extension is a split extension, things are easier. One can do this quicker. There are heuristics in the algorithm which try to choose this series of normal subgroups through the radical in a nice way so that this will happen very often. Yeah, but that is the very rough idea of how we calculate automorphisms, how we can do isomorphism tests. We now have a whole, well, at least behind the curtain, we have a whole battery of routines for calculating with groups. I want to finish by looking at a concrete problem. Bettina already mentioned that problem earlier today, the question of how can we enumerate all groups of a given order. That is a very classical problem. This is already basically that was phrased by Hölder. That's in part behind the motivation for the Jordan-Hölder theorem and so on. Yeah, given an order, find all finite groups of that order up to isomorphism. And if you take abstract algebra textbook, they start by doing this for order 8 and order 10, 12. With 16, as with humans, things become difficult and they don't always cooperate as much as one would want, so they stop. Yeah, and at that point it looks as if you could do always semi-direct products or so, which is simply not true. So what I want to do is to describe basically a very general process for this. There is a more optimized method for P groups, which is the P group generation algorithm. This general method here is basically the same as has been used for solvable groups in the work of Bettina Eick and O'Brien. There is a more recent paper of Bettina, Max Horn, and myself where we extend this a little bit. And the idea is we construct groups as extensions. Our seeding input is simple groups because they can't be formed as extensions from something smaller. And yes, it's again basically the idea behind the solvable radical. Each group is an extension of something of much simpler structure, pun intended, with a module or modules underneath. So in particular, I want to look at perfect groups. So they have been classified before by Holt and Pleskin up to order 1,000,000, but they left out some orders. They went up to order 1,000,000, but these orders I listed here, they left out. And that's basically because there we have factor groups A5, A6, L2, 3, and there are just far too many groups to make this feasible. In the handbook of computational group theory, basically, this enumeration process is described nicely. And what I'm doing is essentially this kind of method. Well, in case you're curious, the result is up to order 2,000,000, and that was just published this spring. There are 15,769 perfect groups up to isomorphism. They will be available in GAP 412. If you're desperate to get them, you send me an email and I can already send them to you now. I verified the results of Holt and Pleskin. There is an amazingly small number of corrections given that their work is by now over 30 years old. Basically, that was one of the oldest results in computational group theory, which people didn't touch again. Yeah, the largest, unsurprisingly, for this is the largest number smaller than 2,000,000, which is a multiple of 60 with a prime power and factor. For that order, that's the largest number of groups. Almost half of them are of this order.
How many of them are superpperfect?
I have not tried this. Probably few, relatively few of them, I would think. Yes, yes. Yeah.
And what were you said there were a few discrepancies. What were the type of causes? Was it
Oh, the type of causes are, yeah, because they, at that time, they couldn't just write a program and say, run over all of it and collect it together. The errors are very obvious. Oh, we forgot that I can form a direct product of these two, of this perfect group with a simple group of another type, and it occurs there. There is nothing conceptually wrong in there. They're the kind of error. I have 50 sheets on my table and I forgot, and one of them falls down. Yeah, so that's why it's really this old result is amazingly correct. So, how does this construction process work? Well, it's in some way similar to climbing mountains. If we have a mountain and we could, for example, imagine which is high, which we want to climb. Well, maybe we can't, so let's start with a smaller mountain to climb. And this smaller mountain would basically be a factor group which is smaller. And then how do we get up a bigger mountain? Well, we lift the mountain up and put something underneath, and then we are higher. Yeah? So that's the generic idea behind the construction. Okay. There is also something in the background which is essentially how any kind of enumeration of somewhat objects with a combinatorial flavor works, and that would be if you enumerate graphs or codes or designs or whatever kind of structure. So we have a reduction process to smaller objects. So for example, if we look at graphs of order on 4 vertices can be obtained by graphs on 3 vertices, what I've drawn blue here, and then by adding a further vertex and adding further edges. Okay. Now the problem is the same graph might be generated many times. So for example, in this situation, if instead of having the straight red edge, I would have added the dashed red edge, I would have gotten an isomorphic graph. Yeah? That away, instead add the other one, these two graphs are isomorphic. And isomorphism tests are expensive. So I want to avoid isomorphism tests. I don't know, in German you say wie der Teufel das Weihwasser. I don't know whether one can say this in French or English. Anyhow, like the devil, the holy water, avoids the holy water. The way I'm doing it is by trying to make the extension process in some way canonical, which typically involves some kind of arbitrary ordering. So what could I do in this situation? I might be saying, oh, if the edges which I'm adding to my old blue graph should come from the vertex with the smallest number, yeah? Then I would only consider the dashed edge. I wouldn't consider this edge unless there is already an edge from vertex 1, yeah? So such lexicographic conditions can take care of some isomorphism properties, and I could consider this as automorphisms of this blue subgraph, taking the automorphism which swaps 1 and 2. I also could have the situation. Here's another way how I could have constructed an isomorphic graph. I might have started with a different subgraph. The blue one now just has these 2 edges, and I add a new vertex and add 2 edges here. That gives me an isomorphic graph. Well, again, lexicography or some kind of ordering will take care of it. I might want to say that I only consider extensions if, say, the number of edges I'm adding to the graph before is minimal, that I couldn't get the same graph in a different way from a smaller one. And through these things, I can severely reduce isomorphism tests. And that's that's the hill on which combinatorial classifications will live or die. It's the isomorphism tests. If you don't get them down, your classification will not run through as far as you want. And basically, if they succeed because the number of, are clever ways of building such extensions to make the number of isomorphism tests small. So, how do we do this? What's the reduction process I'm using? Groups of order n are extensions of groups of a smaller order with a module of the quotient of the orders. My seed would be the radical factors because I want perfect groups and I'm limiting the order to 2 million. The perfect groups of these orders can only be direct products of simple groups. The first situation where I would have something more complicated would be a 5 Reith A5, and that has order much, much more than this. Yeah? So the order limit means the radical factors are just direct products of simple groups. Well, we assume, or at least I assume, the classification of finite simple groups and constructing direct products is easy. So that is done. Now I want to construct the extension, and here what I impose conditions, and these conditions are this kind of arbitrary lexicography, arbitrary in the sense of there is no mathematical reason for it, but they are reasons which will try to reduce the number of isomorphism tests I can do, or I have to do, by saying, oh, in this case, I know I will get the same group already in a different way, and I don't need to consider the one I constructed. So I want the module I put underneath to be a simple module, and actually among all possible simple modules, among all normal subgroups, minimal normal subgroups of the extension, I want it to be of minimal order. I want that the type that then for all possible minimal normal subgroups of the extension of the smallest order, the factor group, which will be also a perfect group, it will have some isomorphism type. It will be isomorphic to some group in the list I had before, which comes from my previous step, that this type is minimal. And yeah, so that's there to reduce isomorphism tests. So starting, what do I do now for such a group? I have a group G, which has, say, order D. It's a smaller perfect group. I construct all modules of suit over the suitable prime of the suitable dimension to get order n. I want the simple modules. How am I doing this? This is using a theorem of Burnside in its variant by Brouwer for the modular case that just says if you have a faithful module and you tensor it up again and again and again with itself, every irreducible module will occur among these tensor products. So I start with one simple module, which I get, say, from a faithful permutation representation. Start with a permutation module, and I just always use the meetx to chop it into simple parts, and I tensor chop, and see what modules I get. That works typically pretty quickly to get me all simple modules. I actually consider them up to action of the automorphism of G, because if I have two modules which are just differ by an automorphism of G, the extensions will end up isomorphic because I'm just changing the coordinates for the factor group. Okay. Furthermore, I can impose a further lexicographic condition that then the isomorphism type of the module would be minimal in a list of modules. In practice, this doesn't matter much for my classification because the vast number of groups are obtained by putting a trivial module underneath. And that's why I also think there will be very, very few super perfect groups. Okay, so there is one more thing which I can do to handle automorphisms. Sorry, not to handle, to handle isomorphism. Namely, let's say I have two such extensions. I have an extension E1, I have an extension E2. In both cases, I have a factor group, have the same factor group here and the same type of module down here. Let's suppose I have an isomorphism which maps this n to that n. Then the isomorphism will induce an isomorphism between these n's and an isomorphism between these g's, and therefore it will actually give me an automorphism of g and an automorphism of n. And such isomorphisms I want to consider especially, and that is through something which are called compatible pairs. Again, they were mentioned already this morning by Bettina in her, I think, first talk or second, oh, don't remember which of them, but they were mentioned. No, this morning. This morning there was the word compatible pairs. Yeah. So, what are compatible pairs? They are pairs of automorphisms of G and automorphisms of N, which are, well, compatible. That means, well, if I take, so if I take an element M of the module, I take an element which is called F here of the factor group G, which acts on the module, and I apply the module automorphism. That is the same as if I first apply the module automorphism to M and then act with the image of the factor group element under the factor group automorphism. This is basically a commutative diagram, if you like commutative diagrams.
It depends on the module.
Yeah, it depends on the module, yeah.
When you say G and N, that
N is here always considered as a G module. Yeah?
So it's all small n.
That this holds for all small m and for all small f. Yes. Yes. Yes, yes, that's exactly. But this takes one line and a commutative diagram takes more space on the slide.
Can you say that V of theta f equal to f?
Yes, yes, yeah. Oh, you can write it in here. You can probably even have, there are probably even slicker ways of representing it categorically. I'm a poor algebraist, and I just, that's the basic version of writing it down. This group acts on the second cohomology group, well, in which, well, basically in the one way how it can act. The second cohomology group, you represent a cohomology class by a 2 co-cycle. That is a map from G cross G to N, and you have the G automorphism act on the G part and the N automorphism act on the N part. Or if you want, that condition basically says that's the largest subgroup of this direct product which actually can plausibly act on the cohomology group. That would be another way of describing the compatible pairs. So this group acts on the second cohomology group, and I only need to consider orbit representatives there. Because if two elements are in the same orbit, I can basically, I know there must be such an isomorphism between the corresponding extensions. How do I get the compatible pairs? Well, I first calculate the module automorphism group of N as a G module. These are basically the ones for a trivial kappa. And then I run in a backtrack search through Aut G. This is very similar to what is happening in the automorphism group calculation, and see whether for a given kappa I can find a new, and that is basically a module isomorphism test. Yeah. Then I need to test these lexicographic conditions. Namely, whenever I construct a new group E, I calculate the normal subgroups of E, which are elementary abelian. I check that n is among them of minimal order. I look for each of them at the isomorphism type of the factor. For one of them, it's G. For others, it might be a different one. I required that this isomorphism type of the factor is minimal. I want that then for these factors, n is of minimal module type. If not, I just discard the extension immediately, because I will know I will construct an isomorphic one again for cases where this lexicographic minimality is satisfied. So what this now does is, why smongst? This was supposed to be amongst, and well, there is, you know what happened if you know a keyboard. Yeah. So if I take all groups and throw them into a bucket and do isomorphism tests, well, if I have k groups, I would have k choose 2 pairwise tests. That's quadratic in k. That very quickly gets expensive. So I want to have to do isomorphism tests, preferably only in small pools of groups, because that will be so much more efficient to do. And sorry, this is my wife calling on Skype, and there I can't even, well, I hope. So I apologize. I apologize, sorry. No, just leave it. It stops. Or move the backpack outside the room. Okay. Then, no, sorry. This is
safe, otherwise you'll try it again.
No, I'll just turn the sound off. I hope she. This is, sorry. Okay. Apologies. Okay. So we want isomorphisms to be in small pools of groups, among small pools of groups, to avoid this k-square blow up. Well, because we took care, because of the lexicography, we know that we will never have to consider an isomorphism where the factor groups are of different kind, or where the modules are of different kind. And because those, so we only need to consider isomorphism among extensions which are constructed for the same G and the same N. And the compatible pairs took care of the situation where the isomorphism maps the N of the one to the N of the other. That means any prospective isomorphism will map this N to another normal subgroup. Yeah? So any will map it to another normal subgroup N prime, such that the N's are isomorphic and the factor groups are isomorphic. So the only groups I need to consider for isomorphism are groups which have two minimal normal subgroups which I basically can't distinguish. And that's few of them. And that's why I only need to do few isomorphisms. And that's why it works.
So this is the automorphism, also isomorphism of the extension that you are describing now.
Yes, in some way I'm also describing all automorphisms of the extension groups. And it's just, since this n is not guaranteed to be characteristic, there could be some which map this n to a different normal subgroup. Yes, and these I need to take care of, but that cannot always happen. That can only happen if there is such an n prime. Yeah? So I can look at E and I can look, can this actually happen? And if not, I know I don't need to consider that case, which is the complicated one. Yeah? That's exactly the situation. And that's why it says here, happens rarely. Okay. Well, still to reduce isomorphism tests, I also need to identify the type of the factor group. I don't want to do this with an isomorphism test, so I'll do this with invariance, isomorphism invariance, number, sizes, order representatives for conjugacy classes, orders of normal subgroups, orders, multiplicities of subgroups of small index, character tables if there are not too many classes. If there are too many, I only look at the values of the characters. I do this before attempting an isomorphism test because, again, otherwise it dies in the number of isomorphism tests. Well, and that gives me the groups. At that point, I get this list of groups for the order, and if I want more, I iterate to the next orders. And that's basically all. Thank you very much.